Okay, I'm sorry for the for the problem. Good morning, everyone. Today I'm going to present our work entitled Asymmetric U-Net for Brain Tumor Segmentation transferred to an independent database. This work was a part of my PhD research and was developed in the Tours University. The outline of this presentation is first a clinical motivation on gliomas, followed by the background in convolutional neural networks and domain adaptation problems. Then I'm going to present the methods and results of the brain tumor segmentation with an application to the Bretonneau Hospital dataset. And finally, the conclusions and perspectives are driven. Gliomas are brain tumors, and all classification divide them between high-grade gliomas, which are considered more aggressive tumors, and low-grade gliomas associated with a better prognosis. The segmentation of these tumors is important for the treatment evaluation and follow-up of the patients, for the radiation therapy planning, and for the image-guided surgery. Commonly, MRI scans are used for the brain tumor segmentation due to its ability to highlight the different tumor subregions. The highly heterogeneous appearance and shapes of these tumors makes this problem one of the most difficult in the medical domain. These tumors have different subregions, namely the peritumoral edema, the enhancing tumor, and the necrotic and non-enhancing tumors. This can be reorganized in these three different subregions that are the whole tumor, that is the union of these three regions, the tumor core, that is the union of the red and yellow regions, and the enhancing tumor in yellow. These regions can be easily distinguished in these three different modalities that are the FLAIR, the T2, and the T1 with gadolinium. In the next section, I'm going to introduce the protagonists of this story, that are the convolutional neural networks. We start from the idea that tumors are different. There are some tumors that are more rounded, others that are more spiky. Even inside the tumor, the tissue has a different texture compared with the normal tissue, and we can find this texture by obtaining the relationship between the pixel intensities inside the image. All these measurements are called radiomics features. And these features capture the information from the images, and they are correlated with genomic data, molecular data, and clinical data, which allow us to classify the different tissues and different tumors. The traditional workflow in image classifications starts with image acquisition and preprocessing, followed by the image segmentation of the region of interest. And then we can extract some features, for example, radiomics features, to train our models. And then we need to reduce this number of features to select the most relevant for the classification problem. And finally, we evaluate our model. Convolutional neural networks have revolutionized this field by replacing these three steps and obtaining useful representations directly from the image and obtaining better results at the same time. Typical convolutional neural network architecture is composed of several layers, namely convolutional, activation, and pooling layers. Convolutional layers are organized in elements called feature maps. Within each feature maps, there are filters or kernels that perform local operations in the previous images and then are transferred to the following layers through a set of weights that are adjusted to minimize the difference between the output prediction of our network and the ground truth. The U-Net architecture proposed in 2015 is the most successful architecture for image segmentation. This is composed of two sections, two parts. The first part is called the encoder, that reduces the size of the image in each level and extracts local features. The second part, called the decoder, recovers the image size and extracts object representation and global information. In other words, the contraction path increases the what and reduces the where, and the expansion path recovers the where. By combining both kind of features from the encoder and decoder, we obtain a highly resolution segmentation map. Convolutional neural networks are a part of deep learning methods that are the state of the art in many different applications. And in particular, in computer vision, they are even exceeding the human performance in image classification and object detection. Despite the great success of CNNs, their use in the real world application is prone to errors. One particular problem with convolutional neural networks is called the domain adaptation problems, which occurs when a network is trained on a bias in a biased database, in a biased domain, and then is evaluated on a different database with a different distribution. We can see in this image that we have different distribution databases for these three different applications. In general, a lower performance is expected when we train, when we evaluate our model in a different database than the one in which the model was trained. To solve these problems, transfer learning strategies have been proposed. So the transfer learning is defined as the ability to apply knowledge learned in a previous task to a novel task. These transfer learning methods avoid to train a new model and reduces the number of training data needed for the new task. In analogy with the human learning, we can say that people often use the knowledge learned for a previous situation in a new one. For example, we can say that acrylic painting will be useful to learn oil painting. Transfer learning can be used to learn a different task using the same database. In this case, this model was trained for object detection, and then this knowledge is transferred for the semantic segmentation problem. A subcategory of transfer learning is domain adaptation, in which we perform the same task, for example, image classification, but in a different domain, with a database with a different distribution. In this work, we evaluated our model trained on BraTS database on a different domain database from the Bretonneau Hospital database, and we reduced this domain gap by implementing preprocessing steps. In the next section, I'm going to present the methods and results for the brain tumor segmentation problem. We propose an asymmetric U-Net which performs the whole tumor segmentation from FLAIR images. And this is called asymmetric U-Net because it contains more residual blocks in the encoder part than in the decoder part, with the objective of extracting more semantic features. And we also replace concatenation operation by using additive skip connections to reduce the memory consumption of our network. And we also use instance normalization instead of batch normalization, since this is more appropriate when training on small batches. To train a neural network, we need a large amount of data. That's why we are using the Brain Tumor Segmentation Challenge database, which is the largest publicly available dataset for this task. And this contains different modalities, T1 with gadolinium, T2, FLAIR, and the ground truth segmentation. But for this work, we are only using 369 patients and only FLAIR and the ground truth segmentation for training and validation or validating our model. And then we are using 125 patients that does not have the ground truth, and we are evaluated the performance of our model in the online platform of the BraTS organizers. That is evaluated in terms of Dodge coefficient. Then we evaluated our model in a second database that is from Bretonneau Hospital, and this is considered as our second test. The DICE metric is a measure of the overlap between the segmentation made by our model and the segmentation performed by an expert medical doctor. In this scale that goes from 0 to 1, 1 corresponds to a better segmentation. To reduce the gap between the BraTS database and the Bretonneau database, we implemented 3 preprocessing steps. First, we register the images, all FLIR images with the FLIR from FSL tool that allow us to take all the images to the same anatomical template from the Sarahi 24 atlas, and at the same time we resample the images to obtain a standard size and image resolution. Then we remove the school by using the brain extraction tool from FSL, and later we corrected the bias field inhomogeneity by using the method N4. And finally, we normalize our images using Z-scores method. These are our training parameters. We use 100 epochs and Adam as optimizer. And as we can see in our learning curves, after about 70 epochs, we reach the plateau. Our learning curves are not decreasing anymore, and the error is not decreasing. And we use a batch size of 1 because of memory constrictions. And we experimented using different data augmentation techniques like rotation, flip, translation, scaling, and adding noise. But the best performance was obtained when we use only random crops and horizontal flips. Here we compare our quantitative results on the BraTS database. We compare our previous or recently published work using an ensemble of 7 models with the second place competitor of the competence of the BraTS challenge. And we can see that our model performs closer to in all the 3 regions, the enhancing tumor, the wall tumor, and the tumor core. And we also obtain a better performance in the enhancing tumor region. And when we compare with our single model and using only FLIR modality with our asymmetric U-Net, we can see that we obtain a lower performance but acceptable in the wall tumor segmentation. And considering that this is a very competitive challenge, we can say that our model performed well. In resume, we obtain a dice coefficient of 87% in the BraTS database, and then when we evaluate it in the Bretonneau database, we obtain an 84% of dice, which is a good performance considering that our model was not trained on this database and was not adjusted or optimized for this new database. But also there is a place for improvement if we reduce the domain gap between these 2 databases. Our qualitative results on the Bretonneau database show that there is no difference between the expert manual segmentation and the segmentation made by our asymmetric U-Net. In conclusion, we propose an asymmetric U-Net architecture to segment the wall tumor, obtaining good results comparable with the state and the art, and using only FLIR modality. This is obtaining similar performance in a different database than the database in which the model was trained is a very difficult task than for the medical domain. Is one of the current challenges. So we obtain a dice score of 84% in the Bretonneau database, which is a promising result for the future inclusion of the CNNs in the real world clinical practice. As a future work, we plan to improve our model's generalization power on different databases by implementing a harmonization method to transfer the knowledge from the biggest databases like BraTS to the clinical databases from the hospitals. And we also aim to explore different domain adaptation methods, such as fine-tuning adversarial-based models, generative models, and reconstruction-based approaches. Finally, I want to thank all the members of our team and to our collaborators, and especially to CONACYT for the PhD grant to develop this project. Thank you for your attention, and I'm ready for your questions.
Many thanks, many thanks to everyone. Feel free to put your question in the chat if you have. I have one, I'm waiting the other. I have not well understood if you segment only the tumor or if you segment first the brain and after the tumor. How do you manage that?
In the work that we submitted for this conference, we are only segmenting the whole tumor, because in our hospital it's very difficult to have all the image modalities that we require to segment all the subregions, because if we want to segment the smallest regions, we need all the modalities, the T1 with contrast, or the T2, and since in the hospitals, the databases are very heterogeneous, the only one modality that we have for all the patients was FLAIR. That is the most common for this tumor evaluation. So we need to retrain our model, because we compare the results with the model that was for segmenting all the subregions and the model used only for whole tumor. So we did both. But for the application to the Bretonneau database, we applied only the one that was trained to segment the whole tumor.
Okay, thanks. A question from Van Lien is, did you compute the dice coefficient for your testing dataset?
No, well, I can do that. I computed for the first validation. I did it, but it's not necessary to do it, because you can obtain these values from the online platform. If you don't, it's very easy to estimate it, but if you don't need to do that, because in the online platform you submit your images and they give you the results of the segmentation in terms of dice. And this is in the test is very important, because we don't have the ground truth, so we cannot estimate it for that set of patients. For the training samples, yes, we can estimate it by ourselves, and we can do it. But
okay. Any other question? So many thanks again, Sarahi, and for this